Hello everyone, welcome to this lecture on electromagnetic induction. In today's lecture we shall discuss about the energy stored in a magnetic field. Now energy stored in a magnetic field, this concept is little bit different than the energy stored in electric field. In the case of electric field, the energy arises when a positive and a negative charge is separated from a neutral atom. The work done to bring about this separation is precisely what is the work done stored in the electric field. Now, for the case of magnetic field, we know that the magnetic force is expressed as F is equal to Q whole into V cross B. All right. So that itself means that whenever you have got a positive or negative charge, say for example, let's in this case consider as unit positive charge, which is moving with a velocity v in a particular direction, and let's suppose there is a perpendicular direction in which magnetic field is there, then the magnetic force always acts in the perpendicular direction to both v and magnetic field. So this is the angle theta. So it always acts in a direction perpendicular to both the magnetic field and the velocity. All right. So that is why if I have to say that if a charge or a unit positive charge is displaced by a distance d, then what is the work done by this magnetic force? In that case, the answer will be precisely 0, because we know that work done is given by the dot product of any force by the displacement vector. So in this case, the force and the displacement vector, they appear in the perpendicular direction, so that I have got the angle between them to be 90 degree. So ultimately cos of 90 is equal to 0, and hence the work done by the magnetic force is 0. So as we used to determine in the case of electric field, the work done is precisely given by the force exerted by the electric field onto a positive charge particle, and that leads to what is the distance that the positive charge particle or negative charge particle traverses in that electric field. That precisely gives the value of the work done. The same concept cannot be applied in the case of magnetic field. So in the case of magnetic field, since work done is equal to 0, so if I have to ask what is the rate of doing work, dw upon dt, that is also given by F dot V, and that itself is also 0. So the concept is little different. So in this case, we however have to remember that in the process of creating a magnetic field or even changing it, electric fields are induced, and this is in accordance with the Faraday's law of electromagnetism that we have already got. Now these induced electric fields can do work in the presence of currents or electric charges. So when the current change to cause a change in the magnetic field, induced electric fields are created which interact with the current to do work. So in the end, what we get that any change in the magnetic field, or in fact if there is a magnetic field which has been created, so one may think that the work done is stored as the energy in the magnetic field. So because of the induced electric field, or because of the change in induced electric field, whatever change has been there in the magnetic field, where or maybe we can say that magnetic field has been a new or fresh magnetic field has been created because of that. So whatever has happened to that magnetic field, it's all due to the change in the induced electric field. So as a result, whatever is energy spent by the electric field in this process, that is gained by that particular magnetic field. So or we can say that the work done in this process of changing or generating a magnetic field is stored as the magnetic energy into the magnetic field. So in this particular class today, we are kind of going to derive an expression uh, of this. We are not going to derive it directly in the sense that we are directly going to derive it from the magnetic field. We are not going to do so. We are kind of going to do a calculation based on the induced electric field, and we are going to say that okay, if this is the work done or rate of doing work in the case of electric field, or rather the induced electric field, then what will be the work done in the case of magnetic field. In that sense, we are going to derive this uh, process or derive this expression of work done. So let's proceed. Let's consider a current density Jr in the presence of an induced electric field E, which itself is caused by the changing magnetic field. So what Faraday's law teaches us that suppose I have got a current flowing in a particular direction and there is a loop just near to it. In that case, there will be a magnetic field associated with this current, which is given by the right hand thumb rule. If you point your thumb in the direction of this current, in that case your fingers will curl towards the direction of the magnetic field. So precisely the magnetic fields will pierce through this surface area and automatically will come out like this. All right, so magnetic field in this particular case points into the page of this paper. And in one of the problem already we have seen that there is an induced current in the anti-clockwise direction. Let's say write it I prime. Now this current, if it is there, in that case induced EMF must be in this particular direction. So this particular induced EMF which has been induced and because of which there is a current into this coil, and let's say the current density of such a thing is given by J. So current density is given by J. So better let us write it that let us consider a current density J, which can be a function of R because R is something position coordinate, you can say, in the presence of an induced electric field. All right. Now, by the way, we have to remember this induced electric field is also caused by some changing magnetic field. All right. Now, to evaluate the amount of work done by the induced electric field, we need to know the charge dq in a volume dv that travels a distance d in some time dt along the direction of the current density. So normally what is the concept of current density? Current density is generally expressed as the current flowing through a conductor per unit area. Now let's say this is a conductor and in that case there is a current which is going in this particular direction and this is the surface area through which the current is coming out. In that case J is represented by I by A, where A is the area of cross section of this wire or this conductor. So what is I, by the way? I is nothing but the rate of change of charge or rate of flow of charge, which is dq upon dt into 1 by A. All right. So if I say that this dq amount of charge is contained within a volume dv and some dq amount of charge flows through a distance d, small d, in time dt, in that case I will be able to write an expression which is dq into d, that's equal to j dv dt. By the way, you don't have to worry about this expression. This expression is nothing but the previous expression itself. So how? Let me show you that. Actually this expression is j, that's equal to dq dt, then I have got d divided by dv. Now this is what? This is nothing but the linear displacement d divided by the total volume. So dq upon dt is nothing but the current, and the linear displacement by volume is going to give you an area in the denominator. So this is nothing but the expression j is equal to I by A itself. So for our benefit we are kind of writing this in this particular sense. So what is the ultimate story to be taken from this is that if dq is the amount of charge uh, which has covered a distance d in time dt within a volume d, we say in that case if j is the current density, in that case we can write this expression. So let me once again write this expression in a new slide and represent it as equation number 1. So let me write this once again. Say dq into d, that's equal to j dv dt. So that's something called equation number 1. Now in that case the work done by the induced electric field on this charge is given by dw, that's equal to e dot d dq. Now where from this has appeared? Work done is generally what we know, work done is equal to force into displacement. Now in this case if dq amount of charge has been transferred through a distance d under the electric field E, in that case, what will be the force acting on the charge because by the electric field, that is E dq dot d. So what I have done, just I have taken dq on the other side and I have written E dot d whole into dq. So that's what I have done. So if I have to write it once again, just let me write d dq, and d dq has already been given an expression by equation number 1. So I'm going to simply write it, and that's equal to E dot, in place of d dq I'm going to write this j dv dt. All right, so let's say this is the work done, dw. Now dw is an elementary work done. Elementary work done in the sense you have got the induced electric field E, because of which there is an induced current I and ultimately the current density J, and in that case a small amount of charge dq is transferred through a distance d. Then what is the amount of work done by the electric field, that is induced electric field, in transferring that charge through a distance d, and that we have denominated by the term dw. So what is the total work done? Means there will not be a dq amount of charge, there will be enormous amount of charges, or what is the total work done in transferring all of charges from one place to another place through a distance t is given by, so that is something we call the total work done. So the total work done is given by W is equal to integration of dW. So that's, we are going to write it as integration of E dot J dV dt, or in a sense we can write it as dW dt to be is equal to, I just kind of want to change it, J dot E, rather we shall write dV, and this is a volume integral. So this is the rate of doing work by the induced electric field on the charges. All right. So if the electric field does this amount of work on the charges, now electric field means which? The induced electric field, and because of that there is a magnetic field which is further induced because of these particular charges or flow of charges. And we know by Lenz's law both these magnetic fields, that means the original magnetic field which has induced the electric field and the newly created magnetic field, they just oppose each other. That means by Lenz's law we have seen that if the original magnetic field has got a northern side towards a solenoid or towards a coil, in that case the coil's front face will also be northern, so that north they repel whenever the magnet is coming closer to the coil, and whenever the magnet was taken away, in that case uh, there is a southern pole which is created. That means basically the Lenz's law itself I'm kind of trying to talk about. So this amount of work is done by the electric field, induced electric field onto the charges to create another magnetic field. So this change in work, or this work done, basically we can say that it is stored as the energy in the magnetic field. So if this is the rate of change of work by the electric field, the same work will be there, or which will be stored as an energy in the magnetic field, but it will be opposite in sign, because energy is conserved quantity. So if somebody is losing energy, somebody must gain energy. If energy is getting transferred from the electric field, it must be gained by the magnetic field, or similarly vice versa. If energy is lost by the magnetic field, it must be gained by the electric field, because we are not considering any decay of energy into our system, through our system. So this work done is negative of the change of magnetic energy. So this work done means the work done by the electric field is negative of the change in magnetic energy, of the change in magnetic energy. So we can write it to be dWb upon dt to be equal to minus of dw upon dt. So in a sense we can write dwb. B here signifies that this is the rate of doing work in the magnetic field. So that's equal to volume integral j dot e dv. So let's say this is equation number 2. All right. Now here we will introduce ourselves to the differential form of Ampere circuital law. Although you may not have encountered it yet, but for the time being you just consider it to be true. So the differential form of Ampere circuital law, so according to the ACL we write it as ACL Ampere circuital law, is written as del cross B. The curl of magnetic field is given by mu naught J, where mu naught is the absolute permeability of free space. So from here I can get the value of J, which is given by 1 upon mu naught whole into del cross B. So if I put back to equation number 2, then we are going to get something like, I'm writing it in the next page. So we are going to get it like dwb upon dt, that's equal to minus of 1 upon mu naught volume integral curl of the magnetic field dot e dv. Now this is very interesting. Here we have got a quantity which contains the dot product of curl of magnetic field and the electric field. So how to resolve this? We cannot do it if we do not know about an identity. So that identity is basically given by, I'm writing the identity here. So there is an identity in the vector uh, calculus that del dot a cross b, if you have something like this, then that is given by b dot del cross a minus a dot del cross b. So in this case we can get this particular thing, a dot del cross b, which is equal to b dot del cross a minus del dot a cross b. All right. So we can also write it as del cross b dot a, because this is a dot product. It doesn't matter whether you take a dot b or b dot a, it is all the same. So b dot del cross a minus del dot a cross b. So here the identity is quite similar to whatever we have here in bracket. So if you just replace a with e, because rest of the thing is same, see we have an expression within the integral which is like del cross b dot e. So it is different from the previous expression only in the sense that in place of a we have to replace e. So it is quite similar, b dot del cross e minus del dot e cross b. So just replace this here so that you get minus 1 upon mu naught v b dot del cross e minus del dot e cross b and whole dv. So if you just resolve it, do one step more, in that case you are going to get 1 upon mu naught volume integral del dot e cross b dv minus 1 upon mu naught b dot del cross e dv. So that's what we are going to get. So this is equation number 3, say for example. So what actually I have done, this minus and minus sign, they have been cancelled, so that is why I have written this as the first term, and this term I have written it as a second term. Anyway, now in this case the first term is clearly applicable under Gauss divergence theorem, which is nothing but the volume integral of divergence of a quantity. So we can clearly convert it into a surface integral. So we wish to write it as del dot E cross B dV, that's equal to integration E cross B dot ds, where this is a surface integral S. So let's write it as equation number 4. So here the volume integral is over all space. Now this volume integral that we have taken, this is over all space, and hence the surface integral is over a surface at infinity. Now this is very crucial point, because if it is a surface at infinity where the electric field goes off to zero, because electric field falls off at large distances, and if you consider the surface at infinity, in that case the electric field will fall off to zero. So we have this particular integral to be vanished, or which is equal to 0. And if it is so, in that case from equation number 3 we remain with only one single term, and that is expressed as dWb upon dt, that's equal to minus 1 upon mu naught integration volume integral by the way p dot del cross E dV. Now once again we have to apply another law, that is the differential form of Faraday's law. Once again you might not have encountered it till now, but so let us write it. The differential form of Faraday's law is del cross E, that's given by minus del B del T. So what you have to do, you just put it back to this particular equation. So is equal to minus 1 upon mu naught integration B dot minus of say let's write it as dV dt dV. So minus minus becomes plus, you remain with this particular term. So if you want to put this B within the differential sign, then you have to put an 2 over here, and you will be remain with this. So in a sense I can say, I can further write it as integration, which is volume integral by the way. I'm not writing this V under the integration sign, which I should write actually. So this is nothing but B square by twice mu naught dV. Alright, so this is what is the rate of doing work in the magnetic field, and this work is nothing but stored as the energy in the magnetic field. So what I can write, the energy stored in the magnetic field is nothing but the volume integral of the term B square by twice mu naught. So this is the final expression for the energy stored in the magnetic field. Many a times we are interested in the expression, what is the energy stored in a magnetic field per unit volume? That means what is the energy density of the magnetic field? This is a question sometime asked. If it is the case, in that case, if you consider this B square upon twice mu naught to be constant, in that case this comes out of the integration sign and you will remain with integration dV, which will give you eventually a volume, the total volume. This normally happens in the case of a solenoid. Suppose you have a solenoid, you know what is the area of cross section, you know what is the length of the solenoid, what is the magnetic field in the central line, actual line of the solenoid. In that case, energy density can be easily found out to be. So the energy density is nothing but b square by twice mu naught. So this is something which is very important. Often we get numerical problems which where we derive this particular thing, or this derivation is of utmost fundamental importance. So please try it back at home, do it by yourself, and try to understand the fundamental concepts hidden. There are two concepts which we have introduced, say for example the differential form of Ampere's circuital law and Faraday's law, which you may not have encountered previously, but that will be dealt with in future classes for sure. So for the time being, you just consider them to be true and proceed with this derivation. All right. So thank you so much for attending this class. Thank you.